He has led professionals to launch bioceramic products into the market. Professor Bikramjit has published more than 300 research articles in the highly reputed international journals, around 25 review articles, which includes more than 5 textbooks, 15 book chapters, and 14,200 plus citations, with H index of 64. The item index 288. We are really fortunate to have such an eminent professional and personality with us to grace this occasion. Now I request Professor Bikramjit Basu to deliver inaugural address. Thank you, sir.
Are you able to see my slides? Hello?
Yeah.
Yes,
Yes, sir. Yes, sir. It's visible, sir.
Is the slide moving?
Yeah, it
yes,
is
sir.
moving.
So,
Go ahead, sir.
So very good morning to everybody and warm welcome to all the participants in this international webinar organized by Periyar University and Icebaa Dental Institute in Tamil Nadu. So at the outset, I used to also thank and appreciate the efforts by Dr. Girija and team, as well as Dr. Gopi and then Vice Chancellor of the university for allowing them to organize this international webinar. This is, I think, fourth webinar that is being jointly organized by our Biomaterial Society in the year 2022, which certainly represents a lot of enthusiasm among the members of the society in such outreach activities. And I'm sure all these webinars will definitely excite the young minds in the field of biomaterials and artificial organs, as well as the regenerative immunity. So I think without taking much time, let me start my scientific presentation. I have slightly changed the title of my talk and little bit theme of my talk because I'm a trained ceramicist who has been working on the engineering ceramics till 2006 or 7, and then slowly moved to the field of biomaterials. So I thought it is important for me also to give lectures on the bioceramics for healthcare. I have posed a question here that where the future lies, and that question I'll try to address towards the end of my talk by showing some of my most recent concepts and ideas to integrate data science with the biomaterial science, a converging concept which is definitely lead to a new theme which we just name it as biomaterialomics. And there is in fact a new paper that has come very recently in ACTA Biomaterials. So yeah, can you all please mute your mic? Hello. Or can the organizer mute everybody else's mic? Yeah. So for the beginners in the field of biomaterials, let me define these two terms. First one is a biomaterial. So it's an important class of materials with proven compatibility with the components of the living system. That means a living system means it is protein, cells, blood, and bacteria. So what you see in this cartoon is that a flat biomaterial substrate on which the eukaryotic cell, eukaryotic means that is the truly nucleated cell. You can see the cell, nucleus of the cell here, and they are trying to establish their adhesion as well as interactions with the biomaterial substrate through the formation of the focal adhesion complexes. Now, those who know a little bit of biology, they would appreciate that cell surface also a large number of proteins, and these proteins will try to establish the contacts with the proteins which are absorbed on the biomaterial surface once the biomaterial is placed in a physiological medium, which definitely would contain several types of several protein molecules. Now, what you see, these string kind of things, these are the actin fibers in the cytoskeleton. Now, any spherical object, their stability would be more and more if the spherical object, instead of establishing the point contact, it will establish multiple contacts, and that demands that the spherical object needs to change its morphology, change its size, and change its shape. And that is what exactly happens when a biological cell tries to adhere on the biomaterial substrate, and this is possible because of the interactions of the cell surface receptors and the proteins which are absorbed on the biomaterial substrate. Now, what is the time scale of this protein absorption, and how they will, what is the spatiotemporal spatiotemporal variation of this protein absorption? Those things cannot be probed by experiments alone, because you need to do the experiments at a much shorter time scale, and that can be probed by using molecular dynamic simulation that I'm going to show you in a few minutes time. Now, throughout this talk, you will see that sometimes I use the term implants and sometimes I use the term scaffold. So it is important for you to know that what is the it is important for you to know what is the difference between these two. What you see in the left side is this femoral ball head, which is a solid, dense implant, which is used in the human body to reconstruct certain part of the human body, that is called in the hip joint, and therefore it should have sufficient mechanical properties. Whereas on the right side, you see the three-dimensional porous architecture, which is typically, you can get it by using microcomputed tomography analysis. And what you see is the three-dimensional porous architecture. And this kind of three-dimensional porous architecture will necessarily allow the blood, cells, and tissues to grow within this porous architecture. And these scaffolds will definitely have lower mechanical properties than implant of similar composition or similar structure, implants of similar composition. However, they will definitely have better biocompatibility. Now, the question is that what is biocompatibility? Biocompatibility is kind of a non-quantifiable property which renders the biomaterial with the most appropriate beneficial cellular and tissue response. And this particular response, it should be specific for a specific applications. For example, a material which is used for orthopedic applications, for example, in a bone implant which is placed in a human body, that may not be suitable, that same composition may not be suitable for cardiovascular applications, simply because that for bone replacement applications, the material needs to support bone cells, connective tissue cells, and so on. But whereas for cardiovascular applications, the material must have good blood compatibility. And also, they should also support the endothelial cells and other cells. So essentially, the biocompatibility needs to be defined in a specific application context. Now, what you see in this cartoon below, that when the biomaterial is placed in the body, and then these protein molecules will be absorbed immediately within a few seconds and so on. And thereafter, these other macrophage and other type of cells will come and adhere on the biomaterial substrate. Essentially, once the cellular signaling processes are set in, and that will lead to the extracellular matrix formation around the implant, and all this process takes place. If you look at the downs in each of the figure, the timeline, typical timeline has been mentioned. So typically, it is 3 to 4 weeks. This biomaterial is integrated, or bone implant is integrated into that human system. And that is the reason most of the orthopedic surgeon, often they do follow up after 3 to 4 weeks after any kind of surgery. Okay. Now, coming to the next point. So essentially, in order to substantiate further that interaction of the biomaterials with the components of the living system, what you see that proteins must be absorbed on the biomaterial substrate. Cells has to establish good interactions with the biomaterial surface, and that has to cell has to undergo morphological changes or functionality changes. Red blood cells should not adhere and should not be damaged when in contact with the biomaterial substrate. Platelets should not be adhering, and bacteria must not interact, or bacterial colonization should not be supported or facilitated by biomaterials, otherwise it will lead to prosthetic infection. Now, cell-material interaction certainly is the first step in establishing, or it is the first step in this overall context of biocompatibility. And what I have explained to you before, that has been mentioned in a more schematic version, and you can see that cell surface receptors actually work like a tongue, what you have seen in the in the household kitchen, and then each of these prong will essentially get attached to these one of the either circle or square. These are essentially showing the different protein molecules, and these different proteins then these prongs will be attached to, and that will lead to better interactions. Now, having said that, this is the next half an hour or so. I'm going to show you some of the research results which we have got when several of my researchers have been working on these, trying to understand the protein material interactions, cell or tissue compatibility parasitites, bioceramic coatings. Maybe in the interest of the time, I'll skip that part. But what I would like to focus and emphasize towards the end of my lecture is the biomaterialomics and translational ecosystem. What is the concept and example? Now, molecular insights into the protein bioceramic interaction. This is a part of PhD work of Subhajit Basu in my group in collaboration with Probal Maiti from Department of Physics at Indian Institute of Science, Bangalore. So what is molecular dynamic simulation? Typically, this is used to solve dynamical characteristics of the complex many-body systems. And this also provides more molecular level understanding at the protein biomaterial interactions. So how this system works? Essentially, you have to initialize the system. Then one has to compute all the forces on all the particles in the system, and you have to use the famous Newton's equations of motions, integrate by Newton's equations of motion, and then calculate the system properties. Calculate the system properties means what is the spatio-temporal evolution of the different system properties, whether it is interaction energy, RMSD, RMSF, and so on. So interatomic potential has two components. One is a bonded component that is called intramolecular, and one is non-bonded component that is intermolecular. So this is the equations where you can see the interatomic potential energy and the potential. So there are different terms. One is the bond vibration, one is the bond bending, one is the torsional term. Then fourth term is the Leonard-Jones potential term, and fifth one is the electrostatic interaction term. Now, when you try to so what we are trying to explore, we are trying to see that how fibronectin protein will get absorbed by the biomaterial substrate, and in this particular case, we have considered the hydroxyapatite or doped hydroxyapatite, which has been extensively used in the biomaterials community. Now, what is fibronectin? Fibronectin is a dimeric glycoprotein. It contains several disulfide linked subunits, and fibronectin is a protein which plays an important role in the cell adhesion, cell morphological changes, thrombosis, and cell migration. So fibronectin has three different type of domains: type 1, type 2, type 3 kind of domains. And what we are trying to see that we have taken the type 3 domain of the fibronectin, and this is essentially fibronectin is a modular protein with homologous repeats of these three polytypical domains, and we have taken the type 3 domain of fibronectin. So this is the molecular dynamics simulation domain. Here you can see the bottom is the hydroxyapatite surface in 001 surface. It is either strontium doped or is a hydroxyapatite, pure hydroxyapatite. And what you see here, that this is the protein molecules, and these proteins are essentially immersed in an aqueous solvent. And then what are the different system properties that we are trying to investigate? We are trying to see that what is the conformational changes or secondary structures of the proteins, how it is changed. Then conformational changes in secondary structure of the protein. What is the RGD sequence when it is exposed to the solvent? What is the attractive electrostatic interaction energy? How many hydrogen bonds are formed? More the number of hydrogen bonds, more is the stability of the proteins which are absorbed on the biomaterial substrate. What is the values of the quantitative evolution of the RMSD values, the root mean square fluctuate, root mean square deviation, and also what is the RMSF values, because higher the RMSF, better is the flexibility of the proteins which are absorbed. Now, any dopant, when you add to the hydroxyapatite lattice, they can potentially substitute either calcium 1 or calcium 2 sites. Now, this is the particular case of the strontium hydroxyapatite because it is known to promote osteoblastic activity and inhibits osteoclastic activity. Osteoblast is the bone forming cells, osteoclast is the bone resorption cells. So, what we have done, we have done the experiments, several experiments, but I'm going to show you next 5 or 10 minutes what is the molecular dynamic simulation results. So when you have done several experiments with different level of strontium doping up to 30% doping in hydroxyapatite, we have seen kind of some of the non-linear trend. Let's say 10 to 15% of doping content, we have seen better cell adhesion is promoted. and beta cell proliferation is facilitated. We are trying to address this particular intriguing observation, that what is the basis for these such observations. So what you see here, that center of mass to center of mass distance between fibronectin and the surface, that how it evolves with time, and typically the time is restricted. The molecular dynamics simulation is 100 to 120 nanoseconds. So that is one of the limitations. We cannot do very large time scale molecular dynamics simulation because it requires an extensive computational power, and many of the software is currently unable to handle that kind of large time scale. So what you see is that minimum hydroxyl fibronectin distance that almost stabilizes at a particular values which is less than 0.18 nanometer, and that is irrespective of whether the dopant content in the strontium dopant content into the hydroxyapatite. And in the number of contacts, that however fluctuates over time. And if you see, more number of contacts typically achieved in case of the 10% strontium. But with more percent strontium, the number of contacts essentially reduced. And you can see this number of contacts within first 6 angstrom, which is very critical from the surface, and that increased to up to 1,000 and so on, which is reasonably or significantly larger than all other strontium doped hydroxyapatite that you can typically see here. Now, what is the different type of interacting residues? Here I must say, more the number of residues, better is the stability of the proteins which are getting absorbed. Here again, you can see 1, 2, 3, 4, 5, 6, 7, 8 residues are present when 10 mole percent strontium is doped to hydroxyapatite, compared to 3 or 4 residues in the other doped or undoped hydroxyapatite, which essentially reconfirms our earlier observations that it is the 10 mole percent strontium doped hydroxyapatite which will definitely enhance or favor better protein material, protein absorption on the biometrical surfaces. And this is how the interaction by electrostatic interaction energy for the different protein residues, which will be which evolves in particular case of different doped hydroxyapatite. And you can see that several protein residues which are there, and their electrostatic interaction energy is almost 0 kilojoule per mole. That is for at least 3 residues. For most of the other residues, it is more negative. So then the next question that we addressed, whether strontium doping will influence the way RGD loop is oriented. But RGD loop is very important because it should be oriented towards the solvent side, not to the material side. Because if the RGD loop is exposed to the solvent side, then only they will favor the interactions with the cell surface receptors. So having said that, what you can notice here, that irrespective of the dopant content, RGD loop is always exposed to this, RGD loop is always exposed to the solvent side, and that is very good to enhance the cell-material interaction. Next few minutes, I'll address this another aspect of the molecular dynamics simulation that is called steered molecular dynamics. Now, steered molecular dynamics simulation essentially are used to validate some of the AFM experiments. Hello, can you please mute your mic? Yeah. So what is steered molecular dynamics simulation? Here you essentially calculate that what is the force that is required to detach the protein from the material surface. And this also is very useful to investigate what is the unfolding, how the unfolding of the protein that occurs in the biological system. So the different terms have been already explained here below, that what is the potential energy, F is the force, K is the spring constant, and so on. Now, what you see that in this particular case, fibronectin, this is the type 3 domain. Here, this for the 10 mole percent strontium doped hydroxyapatite, you see that more forces is required to pull this fibronectin from the surface. What it essentially means that these protein, the fibronectin proteins are absorbed on that strontium doped surface to a much more strongly compared to other strontium doped surfaces. And in this particular case, force constant is around 1500 kilojoule per mole per nanometer. And the highest rupture force, as I said before, that it is observed for 10 mole percent strontium doped hydroxyapatite. What I have not shown you, but we have done also, we have also done a molecular dynamics simulation study to validate some of our experimental results on the electric field mediated fibronectin hydroxyapatite interactions. Now, next we move on to this more on the biomaterials and implants aspect. The first part is more on the scientific aspect. So what I show in most of my lecture is that biomaterials are clinically used for head-to-toe applications of the human patients. And what you see from the top, if you see that, in the top you see that bone flap for cranioplasty applications, then comes dental implants, cochlear implants to treat the hearing disability, ocular lenses, shoulder prostheses. In the cardiovascular implants like stents, which are very commonly used for patients having the artery blockages and so on, pacemakers, total hip joint replacement, then urological implants, total knee joint replacement, bone fixation, and so on. In many of these in many of these surgeries, clinicians in the hospitals in India, they mostly use the implants and biomaterials which are manufactured in the Western countries, and that lead to significant healthcare costs for the Indian patients, and that certainly make the treatment options non-affordable to most of the human patients in India. Now, in this context, what is biomaterial science? Biomaterial science is essentially interactions of the living system components with implantable biomaterials. And implantable biomaterials are developed by utilizing the concept and tool sets from engineering, from physical sciences, whereas our understanding of the living system has been better and better because of our interactions with the medical and biological sciences. So from this discussion, it should be very clear the biomaterial science is at the crossroad of material science on one hand and biological science on the other hand. But there are several other disciplines which also play an important role, and it is essentially playing more and more important role in today's time as well as in the years to come, and that is biomechanics, manufacturing science, human healthcare, toxicological sciences, veterinary sciences. And what is the most important thing is our interactions with the medical sciences. That means the clinicians, because it is the clinicians which essentially define what is the unmet clinical needs. And at the same time, the same clinicians are also actively involved in our clinical studies, whether pilot clinical studies or phase 1, phase 2, phase 3 clinical studies on the biomaterials, implants, scaffolds, and so on. So ultimately, the most important and most satisfying part of biomaterial science, it is indeed contributing to the human health care. Now, in the next 10 or 15 minutes, I'll essentially show us some of our previous research, our past research results in the field of piezoelectric bioceramics. This is the work started by Ashutosh Kumar Dubey, who is currently Associate Professor at Indian Institute of Technology, BHU Varanasi, in Ceramic Engineering Department. So, why this piezoelectric materials is very important. Now, if you look at the structure of the bone, let's say take the example of the cortical bone, or the natural bone as an example. And then if you look at this bone at the different structural levels, like this is the macrostructure, then you go to the microstructure, that's the osteon of the bone, which is 100 micron in size. Then go to the nanostructure where the collagen fibrils and the hydroxyapatite particles are embedded. And then you go to the further topocollagen. So it is the presence of collagen which makes the bone weakly piezoelectric with a piezoelectric strain coefficient of around 0.7. So that also drives significant interest in the biomaterials community on 3 reasons. One, to do research on the collagen and gelatin-based materials. Second, to discover that what is the exact nature of hydroxyapatite, and then what is the different kind of particle size, particle shape that we can mimic, we can produce in a large volume or large scale. And third one, trying to develop piezoelectric biomaterials or piezoelectric bioceramics to mimic the natural bone properties. And if you look at the biological relevance of these electroactive materials or piezoactive materials, if you look at the different human tissues, let's say brain, skeletal muscle, and heart, they are essentially they respond to the electrical stimulation. They essentially represent electroactive tissues. And there are other kind of tissues like blood vessels with the shear sensitive tissues or mechanosensitive tissues like bone, ligament, and tendon, and so on. So if you look at the human bone, as I said before, natural bone essentially represents the graded or gradient porous materials of hydroxyl collagen, and piezoelectricity is known to help in the bone growth, their maintenance, and the fracture healing. Now, in order to mimic these piezoelectric properties in the bone, what Ashutosh has developed in my group is that hydroxyapatite barium titanate composites. And then when we started developing, we're trying to see that, what is the optimum barium titanate content to hydroxyapatite that would be able to mimic the bone properties very, very closely. But what are the challenges that we have to address? One is the retention of barium titanate. We should not allow barium titanate to react with hydroxyapatite, dissociation of hydroxyapatite, and the microstructure of the grain size. So what you see here, that barium titanate with the processing approach that we have adopted is the spark plasma sintering approach. In the spark plasma sintering, what you notice that, if we have used not a single stage sintering, but we have used the multi-stage sintering technique. That means holding that hydroxyl barium titanate at 3 different temperatures, 670, 850, and 950 degrees Celsius. We did not hold at 950. We just heat it and then going to room temperature. And these are the kind of processing approaches when you have used, we could address most of the 3 aspects that what we have mentioned in the right-hand side. So we have also trying to understand that at different temperature by in situ high temperature transmission microscopy, that whether this hydroxybarium titanate, whether this hydroxybarium is dissociated, and what is the evolution of the beta TCP, for example, when you heat it to 950 degrees Celsius. And what we have found in the sintered hydroxyapatite barium titanate composites, we have seen that barium titanate and beta TCP are both retained in the microstructure. And when you have measured the mechanical properties, what we find, particularly I would like to draw your attention to B33, that is the piezoelectric strain coefficient. The bone piezoelectric strain coefficient, as I said before, it is 0.7 picocoulomb per Newton. And what we have found out that somewhere between 20 to 40 barium titanate content, we could achieve the bone piezoelectric properties in the synthetic biomaterials. And there are many other properties that also we have measured, particularly AC conductivity and so on. Again, bone-like conductivity properties like 10 to the power -9 ohm per centimeter, we have ohm centimeter inverse, we have got only around 40% barium titanate addition to hydroxyapatite. So therefore, we have further focused our study. Hello. Can the organizer mute everybody, please? This is the second time it is disturbing. Excuse me.
Yes, sir. Noted, sir. Noted, sir. Please proceed, sir.
No, please. I mean, I'm serious now because it is disturbing me. Okay. So now what we have done that when these materials are weakly conducting, we are trying to understand that whether we can promote further cell functionality modulation using electric field stimulation. So what are the different cell stimulation techniques that we have done? We can use electric field stimulation, but also we can use the ultrasound stimulation and like cyclic stretch, magnetic tweezers, and so on. But electric field stimulation, first thing we did, we essentially used that in-house customized electric field stimulation technique that we have done at IIT Kanpur. And then what we have innovated that how this electric field is delivered to the biomaterials in the culture solution. And what we have done initially, we have done incubation for 12 hours, then followed by electric field stimulation 5 minutes, then 12 hours, the rest period, no electric stimulation, simple culture without electric field stimulation, then again 5 minutes. And that way we go it for that way we do it for a few days in culture, and thereafter we have seen that what is the cell viability using MTT assay. And then what we have found out that after 7 days of the electric field stimulation, and then we have seen that hydroxyapatite 40% barium titanate after electric field stimulation, that cell numbers or number of mitochondrially viable cells significantly much higher than the non-treated hydroxide barium titanate, and even better than that of the hydroxyapatite without barium titanate and control sample. we could pole this hydroxide barium titanate by using the polling conditions, let's say 10 kilovolt per centimeter, and by thermal cycling of 130 degrees Celsius to minus 100 degrees Celsius. And then what we have seen that by polling it, we can use the p-pole surface, n-pole surface, and unpoled surface. And there we can see that in the n-pole surfaces, there also number of cells are much higher. And this is the osteogenic cells that we have grown on the material surfaces, and that has been also reflected quantitatively here. The n-pole surface number of cells is much higher compared to the unpoled and p-pole surface. Now, when you have seen these hydroxide barium titanate in the fibroblast cells, we have also seen similar type of observations. Now, next we have done the animal study. In the animal study, what we have done in the mouse model, in the intra-articular region, we have injected the hydroxyapatite, barium titanate, and hydroxide barium titanate particles. And what we have done, we have seen that after a few days or let's say 2 weeks of study, we have taken the histology sections of the different vital organs and trying to see whether there is any signature of the toxicity, whether tissue architecture at different vital organs is significantly changed. And these vital organs means liver, lung, kidney, and heart, and also spleen. And then we did not see any signature of the toxicity of the hydroxide 40% barium titanate particles. Now, if you look at the much larger magnification histology images of these knee joints or around the knee joint region, you can see there is some accumulation of the hydroxide barium titanate, but associated to that accumulation, we did not find signature of the toxicity or inflammation here. Now, next I'm going to show you that the use of another perovskites in the biomaterials, that is calcium titanate. Now, calcium titanate and barium titanate, these are the two perovskite structures which are less explored in the biomaterials community, and which we find that they have much better potential. But I'm not going to show our biophysical stimulation of the cells experiments on other elastically compliant materials that we have done, but several of these studies are published in Biomaterials Journal in the last 10 years or so. So hydroxide calcium titanate, we have utilized a similar multi-stage sintering technique, but here at different temperature. So what I would like to draw your attention also, this multi-stage sintering technique, multi-stage SPS technique, which we have actually propagated through our research, has been a very effective tool to sinter many of the multi-component ceramic materials in the spark plasma sintering technique. Now, in terms of the properties, it has a good fracture toughness, or essentially calcium titanate addition increases the fracture toughness from somewhere close to 0.7 to 1.8, 1.4 or 1.2 MPa square root meter. And there is also increase in the strength of up to 240 megapascal in terms of the flexural strength. This is the strength, and this is the fracture toughness, like 40% calcium titanate addition, the fracture toughness goes up to 1.6 MPa square root meter. And this was measured using single edge V-notch technique. Now, what is the origin of this fracture toughness enhancement? We have seen in the transmitter microscopy twinned microstructure in the calcium titanate phase. And similar observations also we have seen in the fracture surface. You can see several twins which are essentially clearly observed on this calcium titanate grains, and that leads to a lot of this crack or tortuosity in the materials. In terms of electrical conductivity enhancement, with the addition of 40%, we are getting close to 10 to the minus 8 ohm inverse, centimeter inverse, and that is the reasonable conductivity in the material surface. Now, when you have grown the myoblast muscle cells, this is without any electrical stimulation. Next, I'll show you electrical stimulation experiments. Now, when you grow these muscle cells on these hydroxyapatite calcium titanate surfaces, where the hydroxyapatite has conductivity of 10 to the minus 14 Siemens per centimeter, and then calcium titanate has a conductivity 10 to the minus 3 Siemens per centimeter, and 40% and 80% calcium titanate has 10 to the minus 4 Siemens per centimeter. Now, when you've grown muscle cells without electrical stimulation, we have seen that as the conductivity increases, muscle cells, they are organized in a very nice manner, leads to the myotube formation. And if you see that myoblast density and then myotube density, both are modulated in an electrical conductivity dependent manner. And this is essentially shown here, that first myoblasts, they're determined to proliferate, then align, then fuse, and then they form the matured myotube formation. In all these cases, we have observed the role of substrate conductivity as one of the important parameters to modulate the cell proliferation and differentiation in vitro. Now, next, when we probe further that what is the influence of the electric field stimulation on hydroxy calcium titanate surfaces, we have grown these human mesenchymal stem cells for 4 weeks in culture, and during these 4 weeks in culture, we have used the electric field stimulation for 10 minutes with a 10 volt per centimeter, and then we have found out that what is the increase in the optical density or in terms of the cell number, cell viability. And what we have found at the day 7 and day 14 with electric field and without electric field, there is significant difference. Particularly electric field stimulation promotes more number of mitochondrially active cells on the surfaces. Now, in terms of the ALP activity and collagen content, these are the markers for this osteogenesis. And what we have found, again, around 40% calcium titanate addition, both this ALP activity and collagen, both are kind of significantly modulated compared to non-treated surfaces or hydroxyapatite alone. So this has been marked here. Now, what is our overall understanding is that when you give this electric field stimulation, after 14 days of the stimulation, we have found osteocalcin, alkaline phosphatase, and collagen type 1A is upregulated. After 28 days, we have found that matrix mineralization is enhanced, and then essentially it is leading to more osteoblast-like cells. And this is essentially establishes the important role of electric field stimulation and substrate conductivity together towards the osteoblast cells, towards the differentiation of human mesenchymal stem cells towards the osteoblast cells. Now, we have also trying to validate our in vitro results, particularly the use of conductivity for the bone regeneration. And when we have implanted in the rabbit model, this hydroxyapatite calcium titanate composite, and in the rabbit femur, when you have placed this rabbit femur, these implants, what you have found out that volume percentage of the neobone that is formed after 1 week, in case of hydroxyapatite calcium titanate based materials, it is much larger compared to the hydroxyapatite alone. So what it means that early bone regeneration is possible or facilitated by electroconductive ceramic. But when you go to the 4 weeks and 12 weeks, these error bars overlap, so there is not much difference in terms of the bone regeneration in the between hydroxyapatite calcium titanate. So what is the impact of our research, particularly in this field of biomaterials? And what I've shown you already, that we have been working the musculoskeletal reconstructive regeneration and electrical and magnetic stimulation for regenerative bioelectric medicine. What I have not shown is the dental implants are work and bone flap cranioplasty and urological neobladder. Now, in the dental implants, we have been working on that implant design, right, for the AFIA simulation to various manufacturing routes, as well as finally to the pilot scale manufacturing, clinical studies, regulatory clearance, and so on. So in this particular context, what you see here, once we started the defining clinical needs to biometers and implants to market, the quantum of data significantly decreases. But what is increases, that as the quantum of data decreases, clinical significance of the data also seriously increases. So this is the two contrasting things that is important. So what we believe that, that this so much quantum of data is generated, we need to utilize this data using the emerging data science tools and concepts, and this can lead to much more accelerated discovery of the implants and biomaterials in the years to come. And that led part to the new concept called biomaterialomics. And what is related terms? So the materialomics is the term that Clemens Peterswig and their group has invented long time back. And then comes biomaterialomics that Cranford et al. Also has mentioned that the high throughput analysis biological system components. So either people utilize this in the biological system or people have utilized in the material system. But in both of these earlier approaches, the use of data science and the data science tools were not significantly emphasized. Neither any of the use cases like how to adapt or how to apply these data science concepts to the biomaterial science, that has never been significantly mentioned or emphasized. So what we have recently published is that that you have the biometrical science in one hand, where different properties of relevance like chemical properties, toxicity, electrical conductivity properties, surface topography, they play an important role. And then you have data science, where metadata management, artificial intelligence, machine learning, and statistical approaches play an important role. And you have other side, in the left-hand side, you have a biological omics, like genomics, transcriptomics, proteomics, then clinical imaging and data sets, they play an important role in the patient-specific implants and so on. So it is the convergence of the two approaches, data science and biometrical science, that is the future, and they are the future lines. So what are the key elements of the biometriomics? That is, one hand you have the biometrics development, biocompatibility, performance assessment. On the other hand, we have the modeling, data mining, and e-platforms. In both the cases, you have seen that multi-scale simulation, metadata management, machine learning, and deep learning, as well as different database and online platforms that can potentially help us to develop huge amount of data for a particular biometrical systems, and which can be utilized very effectively using data science tools. Now, there is one particular approach, particularly in vivo studies. Now, this is the Carl Simons group at NIST Gaithersburg. They have done these experiments a few years ago, and one of my former students, Subhodhi Bodhok, is involved in that. And what they have used the combinatorial cassettes where multiple materials, let's say they have used with the experiments with human bone marrow derived stem cells and hydroxyapatite dicalcium phosphate materials alone, and they can use the bone regeneration or the efficacy of these different materials together in a single animal, and therefore these kind of experiments can lead to larger data sets that they have evolved in this particular study. Now, in terms of clinical data, here I must mention that most of the clinical trial data or clinical studies were conducted on the drugs, and therefore most of the widely used publicly accessed database like Bibli database, clinicaltrials.gov, they contain large amount of data that may not be of relevance to the biometrics and implants community. However, some of this data also may be available in those publicly accessible websites which can be of use. Now, what are the challenges? Challenges is the fusion of experiments and modeling. That how you can bring experiments and modeling together on a single platform. And what we believe that this is not an easy task, because we need to utilize several statistically relevant tools like Bayesian inference methods and so on, while analyzing reduced order process structure property linkages and high throughput experimental assays. So we move on to the next one, just to give an example how the machine learning that works. Like when you develop the different compositionally modified same materials as a hydroxyapatite with different strontium content or different iron dopant content and so on. So you start from material 1 to material N. So this material 1 to material N, there is also you measure the different properties. Let's say hardness properties, let's say electrical resistivity properties, let's say cell culture in the cell viability properties and so on. So these are like examples of the property 1, property 2, property 3. Then these properties you can you can learn these properties using some of the machine learning algorithms. Then you have this more number of training data points, and you have more number of learned data points that help us to give the training set in one hand, test data sets in one hand. And these together will help us to predict the properties of an unknown composition of the same material system in an interpolative manner. For example, if you have done these experiments with 0% to 40% strontium doping in hydroxyapatite, and you have done the experiments at 10, 20, 30, 40, but you would like to know 25% strontium doped hydroxyapatite without doing experiments, you can predict using this kind of approach, but you can certainly validate by subsequently performing the experiment 25% that what is the accuracy, what is the predictive capability of your models and so on. So this is one of the examples that we have done in the zirconia and alumina, which is used for femoral head, for example. And here we have used the response surface modeling approach. And if you look at the y-axis, left-hand y-axis sinter density experimental, and x-axis is the sinter density predicted. And if you see that sinter predicted on experiments closely follow with that R-square value is 0.98. So R-square value is 0.98 is fairly good. And this was possible using this multivariate analysis in the response surface modeling approach. And what is beauty of this technique is that on that basis, whatever sintering temperature and time that you can optimize, the same sintering temperature time you can do it for more complex separate components, trimer, acetable liner, and so on. So this is what I was mentioning to you, that you have input variables, process variables, factors and labels, and you have output, that's microsystem property predictions. Then you have a multivariate regression analysis, and then all these things lead to predictive capability of our analysis, and that will essentially lead to the process structure biocompatibility predictions. Okay, so next I'll just show you one of the clinical translational study, that is a cranioplasty study, where we have involved a large number of clinical investigators from two different hospitals, and we have the design and manufacturing team at our place. So what is cranioplasty surgery? This is the decompressive craniotomy. Is one of the most common neurological procedures, and that is used to treat for this TBI, that is traumatic brain injury or stroke itself. And these kind of experiment, these patients, they all these traumatic brain injury can be either due to the traffic accidents or assaults or sudden falls or bicycle road traffic accidents and so on. So what we have done, that for a number of patients, we have taken the CT scan data, then we have identified, and then we have morphological, we have identified the cranial defect area, both in terms of the area as well as the size or thickness of the plates. Then what we have done, we have made this polymethyl methacrylate, which is a regulatory approved material. We have cast this polymethyl methacrylate into 3D printed cranium skull. And then we have freeze dried, we have eco-sterilized, then we have the neurosurgeons implanted these materials in the human patients. Now, in one of the index patients, what you see here, this is the preoperative view, prospective view, and this is the post-operative, and you can clearly see this large amount bone flap area. It can be healed very easily using these 3D printed patient-specific bone flap of polymethyl methacrylate. And the same thing has been validated using CT scan analysis, and their cranial index of symmetry is around 95%. So this is that experiment. This is the surgery that is going on in the operation theater, where neurosurgeons are using the patient-specific bone flaps, which are fabricated and designed based on the CT scan analysis and 3D printed cranium model. And you can see towards the end that they are putting these titanium screws to fix this cranial bone flap into that defected area. So what we are going to propose is that we know, if you trace back the evolution of the biomaterials, we have the first generation biomaterials, which is bioinert. Then comes the second generation biomaterials. Then comes the third generation biomaterials with a functional tissue engineered construct. Then what we are proposing in this recently published review is that this use of the data science approaches can lead to the development of fourth generation biomaterials, 4G biomaterials, which will be driven by the biomaterial mix approach, which will experience the fusion of high throughput experiments, multi-physics models, and data science approaches. Right. So I think I'll just close my talk because of the lack of time. I do not want to spend more time. I would like to acknowledge different government sponsors and private sponsors who have supported our research in the last several years. This translation ecosystem is very important for most of the participants. They should know that who are the people who are working in the different areas in this particular biometrics and implants. And here, if you see that academia and national labs, they are working together in many of these collaborative projects. But academia, they are mostly doing this lab scale development, and national labs, some of the national labs, they do GLP testing. Then comes medical university, dental clinics, and national institutes. And we have the manufacturing ecosystem where MNC, medium scale, and MSMEs, and then startups they are working. And you have the testing and certification with the NABL accredited labs and regulatory consultants working. Now, this ecosystem needs to be much more strengthened in the years to come. where the government agencies will support more kind of collaborative research programs involving some of the key stakeholders of this translational ecosystem. And academia, if you see, that large number of groups are working in India, and in the north, east, south, and west, you can see this huge concentration of these different independent research groups and teams are working in the field of biomaterials. And I would like to mention here one of the key institute who has done pioneering research and who supports a lot of the biomaterials activity in India is Sri Chitra University of Medical Science and Technology in Trivandrum. I would like to acknowledge the significant contributions made by many of the members in this group and who are currently, also serving as assistant professors in some of the IITs or associate professors in some of the IITs in India. Thank you very much.
Thank you very much,
sir.
Professor, for your nice talk.
Thank you so much for your most valuable and detailed insights about the emerging biomaterials and its applications. May I now request our Honorable Vice Chancellor, Professor R. Jagannathan, sir, to deliver his presidential address. Please, sir.
So, good morning, everyone. I am sorry that about late in my joining the International Conference on Emerging Biomaterials for Advanced Applications. I am happy to be here for delivering the presidential address. So, science and medicine brings hope and ensure a quality way of life. The emerging field of biomaterials combines physics, chemistry, and medicine, and more recent influences from material science. In recent decades, human beings face serious bone-related diseases and bone fractures caused by aging, accidents, and high-risk sports, which must be treated with the utmost care. Also, widespread vitamin D deficiency has been shown across all ages throughout India. These fractures are a major public health burden, which decreases quality of life and mortality in women and men. Hence, the development of the next generation bone replacement material is the need of the hour. This could be achieved by the development of biomaterial over the metal